Hey y'all, it's Mr. Boyden back at it again, and here we are today. We're going to be talking about tangents to a circle. So hopefully as we go through this video I can stay on track and I don't go off on a tangent. Alright, let's get to it. Today we're going to start with a little bit of vocab, okay? So what would be fun, maybe if you pause the video, you can look through these 10 terms and try to match them to these images on the right, and let's see how you do. I am going to talk through and write out what most of them mean so that we can see that as in case you don't know what they are, because a lot of them you may not know what they are. Make sure you take notes so that you have that so you can do your assignment. So here we go. Congruent circles. We learned earlier that congruent basically means that two shapes are the same in every way. They may have had some rigid transformation, but they are the same shape. So that would be two circles in this case which have the same size, and that's shown right down here in F. So that's what that's going to be. Okay, for some of these, they may not be as obvious, so I'm going to write down notes about what they are. So for number 2, concentric circles, that's circles which have the same center. It doesn't necessarily mean they're the same size. So like for example, in F, those are two circles that are the same size, but those two center points are not the same. So where do we see two center points that are the same? Well, that's right here in E. Okay, two circles, smaller one, bigger one, same center. All right, what about a radius? This one I expect that you probably already know. A radius is a segment which goes from center to the edge of a circle. Okay, and where do we see that on here? Well, it appears in a lot of them, but it's not necessarily labeled, okay? So we need to be a little bit careful about that. Where is the easiest one to see? That's probably right here from O to E. There's a radius right there, so that would be answer C. All right, number 4. What is a chord? Hopefully what I'm about to teach strikes a chord in you. A chord is a segment which intersects a circle 2 times. Okay, and where can we see that on here? Now, this right here actually is not an example of a chord, or maybe it technically is a chord, but we have a more specific name for that. This one you've probably heard of. That's the diameter. So segment AB, I'm going to go down to diameter and put D for that one. A chord hits twice and is not the diameter. So where do we see that? That occurs right here, D to C. So I'll color code those so they stand out. Okay, and so what letter is that? DC is answer A. So here we go. Let's get the definition of a tangent. A tangent is similar to a chord, and I better call this number 6. So a tangent is a line or segment which intersects a circle, and it doesn't have to be a circle, but today we're talking about circles. That's what we're going to use today. Circle exactly 1 time. Now, that sounds really similar to the secant, although what that means is that the tangent has to be on the outside of the circle. Let's look at why. Okay, if I try to draw a line that hits it exactly once, I say, well, it only hits it 1 time. Well, actually, it's going to hit over here as well, so that doesn't work. So a tangent, so I'm going to label it up, a tangent, and this is my best drawing, looks like this. Okay, it touches at that one point, kind of goes off into space. And that's why we talk about like, hey, you're going off on a tangent. With what that means is if you have the main topic of conversation is the circle and you've kind of gone off on a tangent, you've kind of gone away from the main topic at hand. You've gone off in that direction. So that's a case where we have something that's from math that we actually use in real life in casual conversation. Number 7, a central angle. That one I think is kind of self-explanatory. It's an angle that happens at the center. That's an easy one to match because only one thing on this whole list is an angle. You see the angle symbol right there? Okay, so let's double check. PTR, and that's an angle that does occur at the center of the circle where T is the center. So that is going to be the answer for central angles. That's J. All right, minor arc and major arc. Let's get some definitions there. First of all, maybe we should talk about what an arc is. An arc is just part of the outside of the circle. Okay, so an arc, and usually we have it kind of looks like an arc over the top of it. If I wanted to highlight an arc on the page, one example would be right here. Okay, and that's actually an example of a minor arc. We'll talk about that definition here in just a second. So let's get those out actually. So number 8. Number 8 is an arc with a central angle of less than 180 degrees. Okay, minor, as in it's smaller. Okay, number 9, same thing. In fact, it's so similar, I'm going to copy paste, but what do you think the difference is? This one, it's an arc of more than 180 degrees. And a semicircle, heck, a semicircle is almost the exact same thing. It's an arc with a central angle of exactly 180 degrees. Okay, it's kind of like acute, right, and obtuse, except the number when we're talking about acute, right, and obtuse is 90 degrees. Here, for arcs, you're using 180 degrees, but it's the same exact idea. You could remember that major means big and minor means small. Okay, that might be an easier way to think about it. Let's talk about what these symbols down here mean. So let's color code them. So if I say RQ, it's just saying trace along the circle from R until you get to Q. Now what we do is we trace the shortest path we can that allows us to connect those two. So how big is that central angle? Well, I don't know the actual number, but I can see that it's less than half a circle, so it's smaller than 180 degrees. And that would tell me that it's a minor arc. So G is going to be the answer on that one. Okay, let's look at the next one. Major arc. Well, let's go to H. PRQ. To P, from P to R to Q. How much of the circle is that? To me, that looks like it's half the circle. It appears to be. And so I'm going to put H for semicircle. Major arc, what's next? I should have color coded that. And then PQR. Let's go back to highlighter for a minute. PQR. So I'm going to go from P to R. The reason there's 3 letters is it's telling me which direction to go. There's 2 ways to get from P to R. I can go this way or that way. Okay, but this one is actually telling me which way to go. It says go from P to R and hit Q along the way. So what we're going to pay attention to is how far did I travel? Did I travel half a circle, more than half a circle, or less than half a circle? Well, half a circle would be P to Q. So we traveled more than that, and that would mean that I is the major arc. Okay. Before you go on to this video, pause it and make sure your notes have all the information that you want them to have, because these are terms that are going to continue to come up as we go through this unit. What is a tangent line and how does it relate to the radius of a circle? Okay, we kind of already talked about what a tangent line is. We said it was a line which intersected the circle at exactly one point. In this case, it's point T. I do want to color code some of the vocab here. So we said we have tangent line right here. This line right here is the tangent line. And then it also talks about the radius. So let's get the radius on here. So radius, there it is. Okay, now there is a mathematical fact that we're supposed to get out of this question, and it has to do with this angle right here. A tangent to a circle is always perpendicular to the radius. And that makes a lot of questions easier to answer. The way I'm going to show that here on the picture is by making that a box. So that's always a right angle, and that means there's a lot of cool things that we can do. Before we try solving some actual problems, let's talk about where you might see these or where you might think about tangent lines to a circle. The first application that comes to mind for me, at least, is this toy right here. And this is a toy I used to have when I was a kid. It's called a foxtail ball. And so what this kid is doing is he's swinging this ball in a circle. And eventually he's going to release it. He's going to let go of it. So the ball is moving this direction right now. I don't know if that's clear to see from here. And basically what this allows you to do is throw a ball really far and really high without using that much force or that much energy, because you're building up the energy as you swing the ball round and round. So what does this have to do with tangent lines? Well, what it basically means is whenever he lets go of the ball will continue moving in the same direction as the moment it was when he let go. So right now the ball is moving this way. If he lets go, the ball will fly behind him. And that's one of the things I had to learn when I was a youngster, is I would throw the ball in the wrong direction a lot of times because I didn't know when to release it. So if he wants to throw the ball forward, he'd be way better off to release the ball somewhere in here. If he releases the ball here, the ball is going to be traveling on the path of the tangent line. And so if this is that tangent line, maybe I can make it a little brighter, then the ball is going to end up curving over to, maybe he's playing with a friend over here somewhere or something. Okay, so that's my first application. And as soon as I thought about it as tangent, I go, oh, well, that's easy to understand. Okay. The example that our book gives us, they refer to satellites. Satellites, they go in roughly circular orbits, so it's close enough. And if for some reason they want to deorbit them, or if, I don't know exactly how, but if gravity shut off, they would continue on in the path they were going forever. Okay, and actually that's a lot of how our space exploration works. Is we'll get into orbit. Like the first time we went to the moon, they orbited around the moon, and then eventually they added a little bit of extra thrust and they were able to break free of the orbit. Okay, not exactly a tangent, but really, really close. So let's get one more thing and then we'll answer some questions. Okay, so, and this one I'm going to highlight as well so it stands out a little bit better. Okay, tangent segments to a circle. Okay, so here's our circle. We have a tangent segment here on top and a tangent here kind of diagonally. It says that tangent segments to a circle from a point, so let's get that point nailed down. That point is point N in this example, and these are the tangents that are coming from a point. In this case, they're rays. It says that those are congruent segments. Interesting. So what it's saying is that we can mark these in that way. Take a minute, write down the sentence. If you need to pause the video so you can make your notes look really good, that's fine. Then we're going to take a look at why is that true. Okay, so let's go look at that now. So apparently those two are equal. Let's see why or why not. And to understand, I'm going to get rid of the markings first of all. Okay, so let's start here. What are facts that we know? We learned just a minute ago that a tangent is perpendicular to a radius. So I know that that segment, I know that angle is a right angle, and I know that this angle is a right angle. What else do I know? I know that AE is a radius, and EG is also a radius. And there can only be one radius for any circle, and that means one length, so that means those two segments are congruent. To understand what happens next, I'm going to draw a line, a segment, connecting E and N. Now remember, what did we say back when we learned about proofwriting? What did we say that segment was? Why was it congruent to itself? What we typically said was that was because of the reflexive property. Okay, not reflective, reflexive. Okay, and then what do we know about this triangle? Right now I have angle, angle, side. So triangles are congruent, I'm going to put that in here, by angle, angle, side. And that means that all of their corresponding parts are congruent. So this is one of the corresponding parts. It corresponds to that one if it were reflected over. So I can say that segment AN is congruent to segment GN by CPCTC. Congruent parts, corresponding parts of congruent triangles are congruent. So that's what this theorem is saying. It's saying that this segment and that segment are the same, and this is why. Okay, that's how we would understand or feel really confident that that is a true fact. Because it's good if we can understand why things are true, not just take the textbook's word for it. So let's do an example. Pause for a moment, draw out the picture. In fact, maybe you want to try this one. When you're ready, hit play. All right. In the figure at the right, TA and TG are both tangents to circle N. Okay, I don't even know if it's going to be useful or not, y'all, but I'm going to make a real quick mark right here based on what we just learned. That means those two segments are the same. And maybe that's not useful, but at least it helps us to remember it. All right, let's keep reading. If the major arc formed by the two tangents measures 220, I'm going to color code this. Sometimes the wording can get confusing. Major arcs formed by the two tangents. So we have the two tangents here and there. The major arc is the bigger one. You see the 220 on the picture here and the 220 right there. They say find the measure of T. Okay, so we'll have to think about what else we know. I want to ask you something. If you had a circle and you went all the way around it, what would be the total number of degrees? Hopefully you remember that's 360. The reason that's important is we know the right half of the circle is 220. So to find the left half of the circle, I'm going to go 360 minus 220. Looks like we get 140 when we do that. What that means is that this is 140. Now, since that's 140, that's not T, by the way. We can actually see that angle T is acute. So it's definitely not that. What else do I know? I'm going to take a minute and I'm going to focus on this quadrilateral, and I'm going to highlight it so you can see the one that I'm looking at. There's the first side, there's the second side, there's the third side, and there's the fourth side. Let's think about the things that I know about that quadrilateral. I know this is a right angle because it's the intersection of a tangent, tangent, and a radius. Same thing over here, a radius and a tangent, that's 90 degrees. Do I know what this angle is? Actually, yeah, I do. So if that's 140, this is also 140. The central angle and the arc can both be described by the same number of degrees. So how do I find t? You might want to pause the video again. If you haven't figured it out, you might want to pause and think about it for a minute because it relates to stuff we did a few units ago. We should remember that every quadrilateral, this is a 1, 2, 3, 4-sided shape, has 360 degrees in its interior angles. So from that we can subtract 90, and we can subtract 90 again, and we can subtract 140, that's the third angle. And I'm going to double check it. I think that's 40 though. And sure enough, 40 degrees. So angle T, the measure of angle T is 40 degrees. Okay, and that's it. Let's do another one. And before we do, there's another piece of vocab here that our book wants to make sure that we talk about. We've talked about a segment or a line being tangent to a circle. It's also possible for two circles to be tangent to one another. Okay, and that's the case when they have a tangent line that they intersect at the same point. So maybe I'll zoom in on this example. Okay, here in this picture, I think that you can see that we have two circles. This is a point of tangency right here in the middle. That they have the same tangent line, and they intersect at the same point. So those tangents are, or excuse me, those circles are tangent to one another. This is called externally tangent circles because the two circles have their meeting point on the outside. That's different than internally tangent circles. So one circle is inside of the other in this case, and so that's why we call it internally tangent. They're both on the outside of each other for externally tangent. That's the difference. All right, let's do another example. This is another good chance for you to pause the video and try this one on your own. Hit play when you're ready. Here we go. All right, what can I know in this picture? I'm just going to start by finding information that I can know. I'm going to focus on this triangle down here on the bottom left first. I remember that all triangles have an angle sum of 180. So I already know that there's a 35 and a 90 in there. So minus 35. Oops, that's not a minus. Minus 90. And that's 55 degrees up here. I wonder, do you know how many degrees is in this angle? It's 245. That's the major arc, and this is the central angle. They match. So right here, if I go all the way around a circle, we know that's 360. There's already 245, and we have 55. So I'm going to take the whole circle minus 245 minus 55. Let's see what that is. And I am using a calculator here. You're welcome to do the same. Looks like I get 60 degrees. All right, what else do I know? I'm trying to find x. I know that's 60. I know this is 90. Oh, guess what? If you know the angle is 60 and 90, guess what x has to be? X has to be 30, because that would make it a 30, 60, 90 triangle. Okay, that one's done. All right, now time for our final question of the day. It combines things that are review with things that are new. They ask us, is triangle EGN, that's the bottom one, congruent to triangle EAN, that's the top one, and how do we know? Okay, they're actually asking us to write a proof here. So we kind of already talked about how you'd write a proof for this. I'm going to write out the full proof right now. Okay, and that's going to go like this. First of all, we're going to name these two segments. Segment AE is congruent to segment EG. Oops, capital letters. Got to try to be a good teacher here. And EG because each is a radius. So I'm going to put radii is y. Okay, that's our first claim there. I had also said, and we talked about this earlier, that these are congruent. So I'm going to say, I'm going to name them out as angle. We'll call this one NAE. NAE is congruent to angle NGE. And the reason why is because tangents are perpendicular to the radius. All right. Previously, I had also said that this segment was congruent to itself. So we're going to say EN, segment EN, is congruent to segment EN. I know that seems weird, but it's in both triangles. And the reason why is because of the reflexive property. And so that's actually enough information. That's angle, angle, side, which is exactly earlier what we said it would be. So we're kind of actually just proving a theorem in its entirety here. And so that proves, what do we prove? That the triangles are congruent. So that's what we'll write. The triangle EGN is congruent to triangle EAN. And that's it. Folks, that's all for today's video. Kind of a quick one today, and not too many concepts. Hopefully you enjoy the assignment, and I'll see you next time.